language. Hello, everyone. On. Hello. This isn't on. Hello, hello. Or do we need to do something up here with the sound?
It's not muted.
It's not muted. This is not supposed to depend on that anyway, though, is it?
Probably not, I wouldn't think.
And yours
So
is not doing anything? It should, no,
Well, mine.
it's on. Yeah, so they should be. Oh, whoa, whoa. That's really loud. Can we maybe turn it down a bit? Hello, everyone. This is very loud. I'll hold it. Maybe that's too quiet. Thank you, Tim, our IT manager. Appreciate that. Who is using screens for the first time. Today we have Tim McKay visiting us, and Carol will introduce him in a moment. But there is an agenda which you need that, which you don't. It's kind of going in and out, which you don't need to necessarily look at, but it's in the C Tools resources folder if you care to. And actually, that is where you'll find the link for today's response form at the end of class. Just a couple quick announcements. Thank you all very much for the input on the interim feedback survey. It was really helpful. And we are already trying to implement some of your suggestions. One of the major suggestions we were getting from that is wanting to draw greater connections, greater synthesis among the lectures that we're hearing, which I think we all had the sense would probably be an issue for the class because there is so much going on. So just a couple of the ways that we're doing that. You'll find actually in today's response form a new question that asks you to make a connection. So you might already be thinking about that as you're listening to Tim McKay's presentation. What are some connections that you're seeing to other things we've heard this semester? And connection can mean, as your blog prompt this week says, both a positive connection in that you see a similarity or an agreement of some kind, but it can also be a negative, what we could call a negative connection, that maybe there are two ways of dealing with something similar, but they have divergent views, or there's some kind of a disagreement. So that's just something to think about for your papers as well, that when you're making a connection across presentations for the paper, that it doesn't have to be a similarity. It could be a different kind of way of putting things together. Blog prompt 8 is up. If you haven't seen it yet, we didn't send out an announcement, but it is there. So you can take a look at that. Let's do next Monday, as usual. We realize that is break week. So how do we want to do that? You could do it by, well, actually, no, it's the week after break week, isn't it? So no problem. It's all good. Sorry, I was out of the country last week, and my brain is still not fully back here. The other thing that we want to do with your feedback is, well, you'll see with blog prompt 8 that we're doing some work in the blog, and these were suggestions we got from you in section 2 to help you do some of the pre-writing for assignment 2 and to get feedback from your peers. Since we won't have a formal peer review in the same way as we did for assignment 1, we're going to be using the blog to help with some of we also have one section meeting. Our first class after break is a section meeting rather than a lecture. And so that will also be an opportunity for us to do some group work on the paper. So we'll send out some more information about that for the announcements. This is really going in and out, sorry. Some of you asked when you'll get your next blog post grade, and those we will be posting the Monday after break. And so that's when you'll get that. And at the same time, there we'll also, sometime during that week, give you a sort of midterm assessment on participation and that kind of thing. That was another request that we had. How are we doing? Can you give us sort of a sense of those other smaller pieces and where we stand so that we can make some adjustments if we need to in the second half of the semester? Okay, so I think that's all there is to say in terms of announcements. If there's any questions, we can at the end of class. Sorry, I'm going in and out. And yeah, over to Carol.
Should I use this? Yeah. Hi, everybody. How are you? Am I here? Yes. I am very pleased to introduce Tim McKay, who is the Arthur F. Thurnau Professor of Physics and Astronomy and the Director of the Honors Program at U of M. Are there any honors students here? So you guys all know him. His scientific research focuses on fundamental questions of observational astrophysics and cosmology, such as, quote, what is the nature and distribution of dark and luminous matter in the universe? What processes drive the formation and evolution of structure? How has the global expansion of the universe changed with time? Those are some pretty big questions, Tim. So we look forward to hearing more about them. In addition to astrophysics research, he developed and teaches undergraduate courses in physics, including Physics for the Life Sciences. He is also the chair of the Provost Learning Analytics Task Force and heads SLAM, which is Student Learning Analytics at Michigan, which focuses on the use of data about students' courses and academic programs for the purposes of improving teaching and learning. Please welcome Tim McKay.
Pleasure to get to come and talk about a topic like this. It's an unusual one. A lot of the time when I teach, I'm teaching things that to me at least are extremely familiar, like blocks sliding down inclined planes and things like that. So it's fun to get to come and talk about something that's a little different. Before we start, I would like to get a little bit of a sense of who all of you are. So let's break that down in a couple different ways. First, let me find out how long you've been here. So if you're in your first year, hold up one finger. If you're in your second year, you can figure out the rest of this program. Come on, let me see them. So first and second year students, mostly it looks like a few third year students, a fourth year student, good for you. All right, so we have a little mix. So a lot of you are thinking about the kinds of things that you might like to major in and so on. What about the divisions of the college? So here in LS&A we have a social science division, a natural science division, and a humanities division. Who thinks they either are or might study in the humanities? How about the social sciences? A lot of social sciences. How about the natural sciences? And I can tell there are some undecided people in the room still. And School of Arts. How about the School of Arts? Good. Excellent. All right. I'm used to teaching LS&A students mostly, so. Okay, so I have a little idea who I'm talking to. What I want to do during the next hour is talk about some of my own thoughts about the ways in which new media have affected science. And I don't know if they'll be the same kinds of ways you've been talking about new media with other people, because I haven't been here, so I don't know what they've been talking about. I have some specific things I want to talk about. Before we're done, we'll say a few things about galaxies. That's what's shown in this image here, is a galaxy. And believe it or not, we'll say a few things about birds. That's a common yellowthroat up there in the corner. All right. Before we do that, I want to give you a little background on me just so that you can understand where I'm coming from. I am a physicist, trained as a physicist. Almost all of my research work today is in astronomy. So I go use astronomical telescopes all over the world to look at the sky and understand things about the cosmos. I was never trained in astronomy. So I have an appointment in the astronomy department as a professor of astronomy here, and I never took Astro 101. So one of the things that's true about me is that I have moved from one thing to another in my career, and it's one of the things that you should all imagine will happen to you in your lives, right? As you go along, you may find yourself doing something completely different from what you originally trained yourself for, and that's certainly been true for me. I do teach a lot of large introductory physics courses, and I've been doing that here at Michigan since 1995. I have taught about 30,000 students in my career. Now, I have to say I've done that in this very remote way of having 700 of them in front of me. It's not like I've had this close personal interaction with all 30,000. About 6 or 7 years ago, I became the director of the honors program for the College of LS&A. And what I've most enjoyed about doing that is that I now get to work with students who study everything that you can imagine across the College of LS&A, and it's really been a great thing for me to do. What I want to talk about today is some of my personal experiences that make me interested in the ways in which science work. And as you'll see, the things I want to talk about have to do with the way media interact with the ways in which science works. And so I'm going to talk a little bit about the history of science and my own history and some of the lessons that contains for us about the ways in which media interact with science, and in particular, the ways that new media have really changed science in the last 20 years, because I think they've had just a tremendous impact. Maybe not the way that you would imagine, but it's certainly real. I want to start with something that will look very remote, because it is. This is a paper from a scientific journal taken from 1986. And I want to stress this date up here, October 1st, 1986, and then I'm going to read you this first paragraph. The first paragraph says, roughly 15 different experiments have by now suggested the emission of very high energy gamma rays from the direction and with the characteristic time structure of the binary system Cygnus X3. Okay? The first bit, roughly 15 different experiments have by now suggested. What do you think the authors are trying to convince me of when they say that? Roughly 15 different experiments have by now suggested. What do you think? Anybody?
Sense of consistency, I guess.
Right. They're trying to convince me that this is true. In the first sentence, here it is, stop arguing. 15 different experiments have shown that this is true, right? This is a paper meant to evoke consensus in the field, to say this is a settled question. This paper was published in October 1986. I started graduate school at the University of Chicago in September 1986. So this was something that was a hot topic when I was just beginning graduate school. Let me explain briefly what it means. Very high energy gamma rays. So it turns out that light comes in the form of photons, little particles of light, and the light that we're seeing here in this room is visible light. If you go to more energetic light, you would look at ultraviolet light. Eventually you would look at X-rays, and then you would look at gamma rays, and then you would look at very high energy gamma rays. So these are like crazily energetic bits of light coming from this object, Cygnus X3, which at the time was thought to be and now is known to be a black hole in our galaxy. So this was super exciting stuff. Incredibly energetic radiation coming from a black hole somewhere in the galaxy. Nobody understood how this could possibly be true. And so it was a very exciting discovery, and as you can see, they were meaning to really evoke consensus in the field with this kind of statement. The original detectors that made these measurements, and I tell you about this so that you can see some contrast, were a set of little detectors, each one about this big, about a meter in size, and this is a little map of them. There's a 1 meter scale. So the whole thing was about 25 meters across, not as big as this room. A little set of detectors you could put in your backyard. All right? These kind of instruments were the things that claimed to be seeing these gamma rays from the Cygnus X3 thing. We looked at that, sitting at the University of Chicago, and thought, wow, we could build a much better detector than that. And if it's true, we would be able to see much more than those people have been seeing. So my thesis advisor at Chicago, a guy named Jim Cronin, said, let's do this right. Let's build a really special purpose, very sensitive detector for this purpose, and we will open a new field of astronomy. So you can imagine me as a first-year graduate student getting the chance to go to work on this project that was going to open an entire new field of astronomy. That was pretty thrilling. All right? What did we do? Well, we assembled a team of people, and here we are in about 1989. People from the University of Michigan, as it turns out, and the University of Chicago. We found a place where we could build a really big detector. You can't do that in southeast Michigan because you need enough space. So we went to the desert of western Utah to a place called the Dugway Proving Ground, which looks like about like this for the next couple hundred miles. There's really nothing out there. This is the place where the U.S. Army stores our stores of weapons of mass destruction. You know, we don't let other countries have chemical and biological weapons, but in fact, we have them. And this is where we keep them. All right? It's a place, a proving ground, an army base that's about the size of the state of Connecticut. We built 1,089 boxes that look like this, each of which contains scintillation detectors to detect these particles coming from the sky. We wired them all together in an enormous array. Being witty people, we gave them all names. With 1,089, you have a lot of names to give out. So we had 50 names of famous authors and 50 names of blues musicians and 50 names of, a lot of categories. We needed 20 different categories. They all got names. We put them all out in the desert. This is how we put them in the desert. We carried them out into the desert. leveled the ground, put 250,000 pounds of lead on the top of it. When it was done, this is about a third of it that you can see here. All right, all those little boxes, those are those boxes. They're actually car top carriers that came from a car top carrier company. Every one of them we carried from here out to wherever it was, leveled the spot, laid it down, connected it up with wire. A lot of pieces in this experiment. 250 kilometers of cable, 250,000 pounds of lead, 3 years of construction, 28 semi-trucks. I loaded them all. I am a forklift operator, licensed and everything, because I had to be in order to do this experiment. So we built this whole giant thing. Compared to that little detectors that everybody was seeing these effects from, we were prepared to open a new field of astronomy. What happened instead is that we ended up publishing this paper in 1992, 6 years later, and the key sentence is right here. There is no evidence for a significant excess from any of these searches. So despite the fact that that paper in 1986 was able to say 15 experiments are pretty sure this is really true, they were actually all wrong. All right? What we ended up doing in our experiment is killing a field off instead of opening an experiment. So what do you think are some of the ways in which it could have been true that this statement was true, 15 different experiments have suggested the emission, and that we found nothing? How could this happen? Could science be wrong in this way? Anybody have ideas about how that might occur? Yes. Maybe the original information was false. So there are many ways it could be false. What are some of the ways that it might be false? What are you thinking? They kind of lied, right? So there could be fraud involved, explicit fraud. You know, one of the arguments they're making with this 15 is they're trying to argue it's probably not fraud, because how would you get all those groups to agree to do it together? And for a scientist, that's one of the ways you would judge it. You know, I mean, if other people have seen it, then there's a lot of collusion if it's really fraud. Yes? Yes, that's certainly true. So that by the time we were done, we were able to very robustly test the thing that they were claiming. Any other ideas? Yes? Yeah, their technology is different from the technology we had. There were certainly, when we first came out with our results, arguments that we were wrong. Of course, I mean, these other people had been making these claims for years and really believed it was true. So my sense is that in this particular case, at least, fraud was not an important didn't play an important role, but kind of a self-fraud did. When people find something really exciting, it's both just exciting first, right? And you want to do something exciting. Everybody wants to do something exciting. But it also has important real consequences in their lives. When you discover something exciting, you become famous. You get tenure. You get research grants, right? It has consequences that are substantive. So it creates a kind of slippery slope for people where sometimes they will convince themselves of something that if they could be really removed from it, they wouldn't, right? So all of these things were a factor in this. All of these things, I think, were a factor in the way this happened. And my own sense of why I lost 6 years of my life, and I would say I didn't really lose it. I learned a tremendous lesson in this. Plus, the evenings in the desert are really beautiful. We saw lots of wildlife there. I could tell you lots of great stories about it. But there are some reasons why I think this happened. First of all, I should have recognized that this was a great surprise. And when you see something that's a great surprise, you should put an enormously high standard on whether it's true or not. Right? You should elevate your standard. Something that is an extraordinary claim requires extraordinary evidence before you should believe it. And I think we weren't sufficiently skeptical of these things. There was great excitement and sudden attention for what had been a remote area of science. So these guys who did these kind of experiments, nobody ever paid attention to them until they found this thing. And all of a sudden, everyone was paying attention to them, so they really wanted to stick with it. They wanted it to be true, right? And every time they saw something inconsistent, they had this wonderful excuse. After all, it's a black hole out there emitting this. Well, maybe it goes on and off. We don't know. So they had these nice excuses for why they might not have seen things. And in the end, what really made us do this is that we were entranced by the excitement of this, and we wrote ourselves a narrative about the way the world was that included us opening a new field of astronomy. So we wanted to believe it the same way, in some of the same ways that they wanted to believe it, right? So it taught me a lot of lessons about how I should go about science and about the way science works. You know, there is, think about the way you encounter the science in the media now, maybe in the New York Times or on CNN. You know, you'll hear a report that somebody just published a study that says salt is good for you or salt is bad for you, right? Just one study, and it comes out as if it's true, not as if it's like a little piece of evidence that you should assemble with all the other evidence. So this was a case where it even got beyond that, where a lot of people were assembling evidence and finding this out. So my thesis paper, so that was me up there in the front of this one, was this giant search for the entire northern sky. And the one thing I would say about the work we did on this field is that we did kill the field, and it's still dead. So I think we were right. You know, it hasn't come back to life. It's not become one of these zombie fields. Anyway, so I learned a lot of lessons from this. The main ones are that data is very dangerous, especially when you have something like confirmation bias around. Humans have storytelling minds. You see something happen in the world and you write a story around it. And sometimes that story is right and sometimes it's not, but you cannot resist writing a story around it. So that happens all the time. And it's easy for even earnest people to delude themselves. Not only that, it can happen in a crowd. A lot of people can delude themselves, and for a long time. So just because people have believed something for a long time doesn't mean it's true. Just because everybody believes something doesn't mean it's true. Right? It's a little unsettling to realize this, but it's a fact, and this was a good example of that, those 15 different experiments. But there's another side to the whole story. This was one side, data is kind of dangerous. The other side is the only way we could actually figure this out was to use data. Right? That's the only way we could settle this. What we did is we got much, much better, more extensive, even excessive data. And by doing really skeptical analysis, we were able to find out the truth and settle the question even among people who were enthusiastic about it being the other way. Right? We could win the argument with data. And in fact, there's no real other way to win the argument in science than with data. So we have to use data. Data I consider now my dangerous friend. It's a wonderful thing. You have to be very careful about the way you use it. So what happened after that? Remember, I went to open up a new field of astronomy. I wanted to measure a lot of things. That's what I was excited about. We found nothing. That was very disappointing. So I went off to work on a new project called the Sloan Digital Sky Survey, which was guaranteed to measure 100 million galaxies. And to me, that was a super exciting thing to do, to actually measure something instead of measure nothing. Okay? So that's a little bit of background to think about how science works. Science works by this kind of collection of data that gets shared among people, and then the consensus that emerges when they publish that kind of data convinces people of what might be true. New data then checks that, moves the field in different directions. All right? I want to talk about how we got to the point that we go about science in this way. And so I'm going to digress here now and talk about the media and science. And mostly I'm going to spend some time talking about history of science. I think science is one of, maybe it's the great collective human endeavor. There is no one ever in history that has gone out and looked at the world and learned everything that science knows about it on their own. It's impossible, right? The only way we can know the range of things we know about science is to do it together. Science gets built up bit by bit when a lot of individuals openly and honestly share what they see in the world, what they learn about the world, and they put all that together to form this framework of science. The mechanisms that we have for sharing are what make science possible, and sometimes they drive the science in certain different directions. And those mechanisms partly are technical things. They're media, what you might call media. The first great invention that led to the explosion of modern science was the printing press. It became possible to freely share information at scale, so you could give it to lots of people. As time went on, certain kinds of publications became important. Books or monographs, whole books written about things. Eventually, journals began to appear in scientific societies, and I'll tell you a little bit about that. More recently, commercial journals appeared, and most recently, the internet. And we'll talk about this at the end when I get to talking about the influence of new media. a key element of all this, just having these alone is not enough to make science work. There are social things that have to happen in order for science to work too. These media have to be connected to a social system that gets people to decide to contribute information in the right kind of ways and to digest it in the right kind of ways. And so putting all this together, science is what people sometimes call a socio-technical system. The whole thing, those pieces going together. It's not enough just to have the technology, you also have to have the social structures to make it happen. So thinking about the history of science, you can go back, and especially if you're a cosmologist, you would go back and think about what the world was like in the year 1600. Everyone thought that the Earth was one thing that sat at the center of the universe, and everything else was something completely different. The Earth was made of earth, air, fire, and water. Everything on the Earth was transient and changed with time. The heavens, everything not on the Earth, was perfect, made of something completely different, completely regular, never changing, and so on. This is a Ptolemaic view of the universe with the Earth sitting at the center of the system. Many very beautiful versions of this system were made. Here's another one that was made in 1568 in Portugal, again showing the Earth at the center of the universe. If you look closely at the map of the Earth, you will see there were things people didn't know about it at that time. The west coast in Alaska is just missing. They hadn't been there yet, so they just drew a line across that and so on. But you can see all the planets and the sun itself. This is the sun revolving around the Earth, right? This is the sort of Earth-centered system that science began with. Things shifted over when Nicola Copernicus wrote a book describing a different system, the Copernican system, which has the sun sitting at the center and the Earth orbiting around it with the moon orbiting around the Earth as it goes around the sun. Right? So you know a little bit about this story, probably most of you. This was in 1543. It's at a time when people are starting to publish things, starting to share their scientific knowledge in a new kind of way. What do you see here? This is written in Latin, so it's intended for a very narrow audience, just the people who could read Latin. It was actually published in a very narrow kind of way, for a very narrow world. This is the world that Galileo was born into, a world in which Copernicus had started to write about this kind of system. And what really changed science, what really launched modern science, was the invention of an instrument, a device for magnifying your view. He promptly built a version which would magnify his own view by 3 times and improved it to 30 times. It also made his eye bigger so that he could see fainter things. A very important role of telescopes as well. Works just as well for owls as it does for telescopes. So Galileo did this, and as soon as he had an instrument that could enable him to see things he'd never seen before, he immediately discovered an enormous array of things. This picture is meant to give you a sense of what a telescope like Galileo's would do. This is looking out over the roofs of Paris. There's a little telescope. And there's a scene out here. You can see it without the telescope, right? But there's a lot of detail in that scene that you can't see without the telescope. If you were to magnify that scene by 3 times, you would see a lot more detail. And if you were to magnify that scene by 30 times, you would see vastly more detail. In fact, discover things that were completely invisible in the original image. So when Galileo built his telescope, this is what happened. He just had to look anywhere on the sky, and he could see things that no one had ever seen before. Didn't have to be all that sophisticated. All he had to do was go and look. And as soon as he did, he started discovering amazing things. And as soon as he discovered those amazing things, he raced to tell everyone about it. And this is part of the socio-technical system of science in which media plays a central role. It's no good just to learn something for yourself in science. You're actually not doing science if you just learn something for yourself. Doing science is learning something for yourself and then sharing it with everybody else through effective media, through ways which actually reach all the other people in the world. Galileo was born at a time when this was starting to become the thing to do, to share what you learned with other people. You could get more out of sharing what you learned than you could out of keeping the knowledge private. All right? And that's something that science had to happen, a system that would reward that. It turns out that here in the University of Michigan Library, we have a letter written by Galileo in his own hand. You can go to the library, and if you're asked nicely, you can actually hold this piece of paper in your hand that Galileo wrote on. Pretty amazing. So that would be amazing if it was any letter that Galileo wrote, but it turns out the letter we have is really important. It does two things. First of all, it's a draft of a letter that he sent to the Doge of Venice. The Doge of Venice was the political head of the city of Venice, which at that time was an enormously powerful place. He says in that letter, I've invented this wonderful new thing, and you're going to want to buy it, because it will enable you to see your enemy's ships before they can see you. He's basically saying, I have a military contract for you. And the Doge was no fool. He bought the telescope and hired Galileo and paid his salary for the rest of his life. Okay? But so that's what this letter on the top talks about. I assure you, I shall keep this new invention a great secret and show it only to your highness, right? So it's quite an interesting letter. The letter itself would be interesting, but on the bottom is something even better. On the bottom are pictures drawn by Galileo of his first observations of the moons of Jupiter. All right? And if you blow those up, what you can see in these are pictures where he's showing the moons of Jupiter around the planet of Jupiter, and what he noticed is that they change from night to night. At first, he had no idea what that meant. There were these three little stars next to Jupiter every night, and Jupiter's moving across the sky, right? But those three stars go with it, and he didn't know what it meant. They were traveling with it somehow. And then down here on the bottom, you can basically see him figure it out. Right? So after a couple nights, he sees them lined up this way, and he's like, oh, they're going around Jupiter. Jupiter is a little solar system traveling around the solar system. All right? It's an amazing discovery. It was the strongest evidence for the Copernican system that had ever existed. And it sits in a library a couple hundred yards from here. It's a pretty cool thing. He raced to publish this book called The Sidereal Messenger, still written in Latin, still written for other scholars. He published it in 1610, a few months after he invented this telescope. Like as fast as he could, he raced to get this into print. The printer was across the street from his house. As each page came off the printer, he read through it to make sure it was correct. Right? I mean, it was really a race to get this out as fast as he could. In it, he discovered a ton of things. He discovered that the Milky Way was made of stars. No one ever knew that before. It was just milky. Right? So he immediately, as soon as he pointed the telescope at the sky, discovered millions of new stars. Pretty great evening to have. He discovered that there were mountains on the moon. Remember, most people thought everything in the sky was perfect at that time. And he said, no, the moon looks just like the Earth. It's got mountains on it. That's what this is showing. You see the shadows? It's showing that it has surface features, right? He discovered the moons of Jupiter. He discovered sunspots. He discovered that the planet Venus has phases, another piece of evidence that Venus was going around the sun. All right, amazing thing, an amazing book that he published. And he raced to publish it because science was becoming a thing where that's what you did, was to share what you learned as fast as possible. All right. So that's a really important moment when science starts to do that. It's often driven by the creation of new tools like this, so the telescope. Galileo also invented a microscope at the same time. But there are these socio-technical tools that are at least as important, and a lot of them were born around this time. Things like learned societies, groups of people who get together and say, what we're going to do is we're going to come together every week and talk about what we learn. You go do experiments, and I'll go do experiments, and you go do experiments. We'll talk about them. We'll share what we learn, right? So those happened in a bunch of ways, some very important ones, some of them chartered by leaders of countries, and some of them more informal. The three big ones in the early part of the 17th century, the Academy of the Links, which Galileo was in and which he always was very proud of being part of. The Académie Française, the Royal Society in London. Some of these, actually all of these societies still exist today. And they fostered the idea of an open experimental method, that the way to find out what's true is that you do the experiment, and then I'll do the experiment, and then he'll do the experiment, and if we all see the same thing, it's true. That's what science has really turned into. And these guys were creating this in this time. So this is the guy, Federico Sesi, who founded this Academy of the Links in Florence. And then there's the Royal Society in London, which this is its first publication. Here's its royal crest, and you can see its motto written on here, nullius in verba, which means don't take anyone's word for it. Right? Go and find out for yourself. And this was the Great Enlightenment idea, that you shouldn't use authority to decide how the world is. You should look at the world and figure out how it really is. Don't just read about it in a book and say, well, the book says this is what it is. And then this is the Académie Française, very similar but better dressed. There was lots of informal learning going on at the time. And in fact, it might not be clear to you, but universities played very little role in the scientific revolution, or really in the Enlightenment. Because universities at the time were very, very conservative organizations where people were taught the classics, they were taught Greek and Latin, they were taught religious topics, and none of the science that was being done was being taught in universities at the time. There's a big transition in the 19th century when universities become things that become generators of new knowledge. Not true at the time. So these scientific societies helped to create the research structures that happen today. And science began to become of popular interest. People in the rest of the world started to read science. That happened in part because people like Galileo started to write in vulgar languages like Italian instead of in Latin. They started to write for everyone instead of for just a group of scholars. So he wrote this Two New Sciences in 1638. Just last year, I discovered a book that's become my very favorite book, certainly my favorite book from the 17th century, called Conversations on the Plurality of Worlds, written by this man named Bernard de Fontenelle. And it is a summary of what was known in science about astronomy, at least at the time. It became incredibly popular. It's led me to learn about this amazing guy, Bernard de Fontenelle, who some people called the most civilized man ever. Right? It's a pretty good title to have. He was a big literary figure and poet in the early Enlightenment, and he popularized this Copernican system in this book. He had this wonderful title of being the perpetual secretary of the Academy of Sciences, which I think, how can you beat that? The book he wrote is interesting because he taught science through dialogues. So the way he taught science is he told a story in this book about these two people, this young man and this very beautiful young duchess, who just happened to be stuck together on a country estate. Nobody else around. Every evening they would go for a walk in the garden, very beautiful French gardens, and he would tell her about what had been learned in astronomy recently. And she would ask him questions back. So this is a way of teaching science which allowed you to talk about what was known and have people raise objections. But wait, how could that be true, right? And then have those objections be discussed. It's so much nicer way of reading about science than reading a textbook where somebody just says, this is what we know, right? It's the most charming book. So if you have any interest in this kind of thing, you should go look up this book and read a little bit of it. Of course, it's all available online. Dialogue is a really effective mode of writing for science. And you can see here the Copernican worldview, the sun here in the center of the system. Here's the Earth with the moon going around it. Here's Jupiter, here's Saturn. You can actually see the little shadows behind them because he was explaining to her how eclipses work. It's a really delightful book. Its whole last chapter is about all the people who live on all these other planets, because he's quite confident that there are people who live on all these other planets and that every other star must have planets around it with people living there too. It's really an amazing book. So time went on and publication really took off. This is a sort of a picture of the European output of printed books from the 15th to 16th to 17th to 18th centuries. Publication really taking off so that all the information that a few people know is now being spread to many people. So imagine you're thinking about how science advances. Somebody learns something cool. If they tell a few of their friends, okay, maybe it grows a little bit. But if they can tell everyone in Europe, then someone out there will pick up on it and do something with it, right? So this ability to spread that information is the key to making a scientific system like this. And the reason that it spreads so fast now is because we have much more powerful tools for that. In this period, people started to build careers, becoming famous for telling everybody else what they learned, and journals began to appear. This is one of the very first regularly published journals, which is still published today, the Philosophical Transactions of the Royal Society, giving some account of the present undertaking studies and labors of the ingenious in many considerable parts of the world. It's a pretty great title. And this is their volume 1 from 1665. What was in that first volume? This is the table of contents from the very first volume, and it's really fun because they talk about everything. A spot in one of the belts of Jupiter. Anybody ever heard of the Great Red Spot on Jupiter? It's a storm that's 400 years old on Jupiter, and they were talking about just seeing it for the first time here. The motion of a comet, an experimental history of cold. People didn't understand anything about heat at this time, so they were doing experiments on cold, and that one contains a quote that I really love. This treatise will be dispatched within a very short time, and would have been so, ere this, if the extremity of the late frost had not stopped the presses. So this study of cold was delayed because it was too cold to publish it. An account of a very odd, monstrous calf, the new American whale fishing ground in the Bermudas. They would write about whatever. They were just learning new things. Okay. At the time when Galileo was writing, in the beginning of the Royal Society, science was not a well-established thing. The word wasn't being used yet. People talked about natural philosophy. And originally, physics was kind of all of natural science, anything that was happening in natural science. And anything that was not physics was metaphysics. So when we use that word metaphysics, we mean something beyond the natural laws of the world, something that's not just the natural laws of the world. Other disciplines began to emerge, and I've listed the first time that some of these words were used, so geology and chemistry and biology, modern medicine. The word scientist wasn't actually invented or used to describe a scientist until 1840. And it was invented specifically to describe a new thing, a person who was paid to do this work, to be a scientist, right? Now, of course, we have this whole array of different sciences, but really they're all part of the same picture. And that's what was recognized at the beginning. There really are only laws of nature, and all these different sciences are part of that. Physics plays a kind of special role in the sciences, and I wanted to say a little bit about that, how you should think about who a physicist is. Physicists have a lot of different traits, but one is that they tend to focus on fundamental things. So if you start out with a complicated question, a physicist will first say, let's ignore all the complications and look at the most basic part of this. We do that because it proves useful sometimes, but it also sometimes leads you to really miss the main point. So physicists don't have the perfect attitude for this. Physicists tend to like to quantify things, to measure them precisely, and to model them mathematically. And they tend to think in reductionist ways. What's really going on is the most basic part of it, and the details are not so important. There's a big argument in physics about that, about whether a reductionist view is more powerful than a view that looks at emergence, about the things that come out when there's more going on. This is a comic called xkcd.com. Anybody read XKCD? It's a pretty popular web comic. Very on target about a lot of things in science. So a sort of typical way a physicist would say something to a liberal arts major would be, oh, you're trying to predict the behavior of whatever. Just model it as a whatever and add some secondary terms for whatever. That's easy, right? Why do you need a journal and all that, right? So that's the sort of attitude that I think people think physicists have. Everything is really fundamentally simple, and why should you get all excited about it? This is another XKCD comic that talks about different fields of science arranged on a scale of purity. So there's sociologists on one side and psychologists who say sociology is just applied psychology, and biologists who say psychology is just applied biology, and chemists who say biology is just applied chemistry, and physicists who say it's just applied physics. It's nice to be on top. And then the mathematicians who are somewhere way over here and nobody really knows how they fit into the picture. But really all part of one thing, just different views of different areas of what's going on in the physical world. Among physicists, there are three major divisions of physicists. There used to be only two, but there's a new one now. So the two used to be experiment and observation. I'm an experimental scientist. I'm not that interested in just thinking about how the world ought to be. I want to find out how it is, right? So I go out and look at the world to try and find out how things really are. Then there are theorists who would rather sit around and think about how the world ought to be. And then eventually we'll find out whether it is that way or not. But that's what they want to do, is think about how it ought to be. The new thing that has emerged in the last 40 years is computation as a really important part of every kind of science. First in physics perhaps, but now really invading every kind of science. And so physics is really more of an approach than it is a list of topics. Physicists feel authorized to weigh in on anything that they want to. And this is something that shows you kind of the difference between experimental scientists, or maybe scientists at all, and normal people. You pull the lever, you get an enormous shock. What do you do then? Well, normal people say, I shouldn't do that. And scientists say, I wonder if that happens every time. Right. So we get into the 19th century, science is starting to be invented, and people start to try to create what will become professional science. And this guy, Aldous Huxley, really played a very important role in that in the latter part of the 19th century. He was a person who, unlike the scientists before him, he wasn't rich. So most of the scientists before him, people like Charles Darwin, were people who were wealthy and just chose to do science. They didn't have a job doing science. He needed a job, so he wanted to professionalize science. And some of the other people he worked with, like Joseph Hooker and Herbert Spencer, John Tyndall, they created this club they called the X Club. It was largely created to defend Darwinism right after The Origin of Species was published. And they got together and founded a journal, a new journal, not part of a royal society, called Nature in 1869. And this journal launched modern scientific publishing, and it remains at the center of modern scientific publishing. So at that time, there were all kinds of magazines and newspapers being published. That publishing technology let people spread information really fast, as did things like having a system of mail that allowed people to send stuff all over the world really quickly. It's amazing what the Royal Mail did in the early part of the 19th century. Someone like Charles Darwin could be traveling the world, going to the Galapagos, and still be in regular contact with England. It's kind of crazy that they figured out ways to do that. But he was able to send letters back and forth on a regular basis, even when he was traveling around the world. And that enabled them to exchange information at an enormous rate. At this time when modern science was being born, scientists were also appearing, experts, who would start to speak among themselves, removed from everybody else. Right? So the discourse starts to change from one where Charles Darwin would write a book like The Origin of Species that everyone was meant to read. And in fact, everyone could. Now you start to see people publishing in journals like this for other scientists. They start to make themselves professional by writing in a way which no one else can read. Right? They actually are creating their community by separating themselves from everyone else in these journals. So a new kind of professional core, they wanted a rapid response. They wanted peer review. They wanted to know that if something showed up in Nature, it meant something. It was really right. So they founded this journal in 1869, and it was different from what it is today. In fact, the very first thing in it is a bunch of aphorisms by Goethe, selected by Thomas Huxley and placed in this. But then you see different kinds of articles in that first edition of Nature. Their goal, still stated in the front of it every single time, gets across the idea of what scientific publication is supposed to be for. The objective which it is proposed to obtain by this periodical may be broadly stated as followed, and there are two things. It is intended, first, to place before the general public the grand results of scientific work and scientific discovery, and to urge the claims of science to move to a more general recognition in education and daily life. Remember, I told you at this time people were not learning science in universities. These guys were advocating for learning science in the universities. That was a part of it. Secondly, to aid the scientific men themselves by giving early information of all advances made in any branch of natural knowledge throughout the world, and by affording them an opportunity of discussing the various scientific questions which arise from time to time. So it's explicitly for sharing this information as fast, as accurately as possible. And that's really what publication still is about in science, about sharing information as fast as possible. Nature is still published. These are some of the recent covers from the journal Nature. It comes out every week, a big, thick volume of Nature. It is the highest impact journal in the world still, meaning that more people cite more papers from Nature than any other journal. It still plays a central role. During the 20th century, this peer-reviewed journal model became canonical, meaning that if you had a piece of science and you wanted it to become a piece of science, the only way to really do that was to put it in a peer-reviewed journal. Right? It became the way that we would decide a scientist was a scientist. Do you write peer-reviewed articles? If you don't, you're not a scientist. How many do you write? That's how we'll know how good a scientist you are. Right? It sort of became a really integral part of the system. These peer-reviewed journals had some key features. There was limited access to them. So they actually, although they were intended to spread things, they also cut everybody off. Like most of the people in the world don't have a subscription to Nature. That's because it costs a lot of money to have a subscription to Nature. Right? So a lot of people were cut out by it. They became increasingly specialized in both content and style. Harder and harder to read these things. Right? If you read papers from the early part of the 20th century, they're really nice to read. You read them now, almost impossible. Right? And publication became this measure of productivity. This is a figure from a paper written in 1963 that was talking about the growth of big science. And it just shows you how rapidly papers are being published in all these different fields, how rapidly it grew in the early part of the 20th century, and then how it's continuing on, doubling about every 15 years, the number of papers that have been written. So this whole thing became an engine of churning of publication. Still all happening in these paper journals that would go on library shelves and were accessible only to people with access to those libraries. So why do we need journals? Journals have a bunch of functions. One of them is that they channel communication and draw people's attention. So journals are about different topics. I would read the Astrophysical Journal. Somebody else would read the Journal of Neuroscience. So they're filtering what's happening out in the world. Many people believe that peer review is a very powerful test of both the quality of a paper, is it important, and its accuracy, is it right? And there's no question that peer review helps a bit with accuracy. But remember back to the story I told you in the beginning. 15 experiments had all found results that suggested this thing that was really wrong. All published in peer-reviewed journals. Peer review is not a magic bullet against inaccurate conclusions. It's one simple step that can help with it, but it isn't magic at all. There are lots of other potential problems with peer review as well. Like, if I write a paper and I send it into a journal, they want to send that paper to an expert in order to review it. So who are the people who are most expert in what I do? My competitors. Are my competitors sometimes going to be tempted to criticize my paper in an unfair way? Maybe. They're my competitors after all, right? So it's not a perfect system, but it is a system that's at the center of the way science still runs. Journals also handle the distribution of new results. They try to do it rapidly. They try to do it efficiently. I would say they fail in both of those things, especially by modern standards. So it might be that we don't really need these journals anymore. And the first thing that I asked you to read for this was a history of the archive project. And I hope you all read it. It's very amusing, actually, because it's also almost on the side a history of the internet and people's experience with it. What was it like to be a scientist in 1980 compared to being a scientist in 2010? Really interesting kind of change. This archive project almost undermined the journal system, and in some ways it did. So I want to talk about that a little bit. The archive server was about preprints. Journals, although they try to be fast, have never really been very fast. Review takes a lot of time. In most journals, if I send a paper in, I might expect to hear back from the journal in 6 months to a year. And then I would send a revised version back, and I might hear again in another month or two. So by the time the paper is published, it might be a year and a half after I finished writing it. Pretty slow in the modern world. I mean, stuff is supposed to happen overnight, right? So that's a problem. They do work to format it and everything, so it ends up taking at least a year for a paper to typically come out after you send it in. As soon as copying became possible, mimeograph machines were the first ones. As soon as copying became possible, people started sending their paper in, and then instead of waiting a year and a half for it to get published, they would print some copies and send it to all the elite institutions where they wanted people to know they were doing this good work. What it meant is that those institutions, places like Michigan and Princeton and Harvard, would get access to the latest science a year or a year and a half before anybody else. That's a great thing if you want to be an elite institution and stay an elite institution, right? It's a closed network of secret information going back and forth among people, but not very good for science in general. Remember, the purpose of science is to get it out there. So once there were electronic versions of paper, this kind of giving it out to your friends accelerated. That was happening more and more. The archive server was like a monkey wrench change to that whole system. It opened up the opportunity for everyone in the world to get preprints instantly and equally. And it was a real sea change in the field. So this was born. It was first run on a server that had the website xxx.lanl.gov. It was so early in these days that other websites had www, and he decided he would call his XXX because it came after W, right? It was just a, all right. And he created this thing that was intended to democratize access to new science. So the purpose of it was to collect input from anyone who wanted to send something in. No review at all. You just send something in, we'll send it back out. He made it immediately available to anyone who wanted to read it. All right? So he talks about it in this paper. It was initially an automated email server and then became an FTP server. You could go and get these papers. Very simple thing. Originally intended for about 100 submissions per year from a small subfield of high-energy particle physics. It got 400 submissions in its first half year. The submissions were initially planned to be deleted after 3 months, but by popular demand, nothing was ever deleted. So every paper that was ever sent in was kept forever. All right? It was renamed in 1998 to this archive.org, and it has since accumulated about 700,000 papers as of 2011 and receives 75,000 new submissions a year. The papers are downloaded millions of times every year. It's a flood of information going out instantly, overnight, to people all over the world. My first archive paper was born in 1995. This is it, Weak Lensing in the Sloan Digital Sky Survey with my friends Albert Stebbin and Josh Freeman. Since that time, all my papers go into the archive, as do the papers of most of the people that I know. So this article that I asked you to read about it, it's a really lovely article because it also talks about the history of the internet a little bit. There were lots of concerns about the archive when it first came out. The biggest one was, oh my God, you couldn't read those papers. They haven't been peer reviewed. Right? There was this magical standard applied to peer review. So they're not peer reviewed in advance. But think about what happens. If you send a paper into the archive, who's going to see it? The peer reviewer at the journal? In fact, everyone in your community is going to see it. So it's like mega peer reviewed. You don't send something there unless you really believe it. Because if you do, you look like a fool. If you send a paper to a journal that you don't really believe, well, maybe the peer reviewer decides it's bad and won't publish it. But it doesn't ruin your reputation. So actually, this is much more public than sending something into a journal. And so people actually very quickly adopted a pretty high standard for what they would send in. People just didn't get that idea that this would be the case. It's still the case that almost everything that goes to the archive is eventually in the peer-reviewed literature. And I would say this is mostly a socio-technical problem. Here at a place like the University of Michigan, when we're deciding whether to give tenure to a scientist, we really do count how many peer-reviewed papers they've published. I'm not saying that's necessarily the right thing for us to do, but we do it. So everybody wants their papers to appear in peer-reviewed publications, because otherwise they won't get the credit. They might not get the job they want to have. It's not really necessary for the science for that to happen, but it's necessary for the society. Everybody thought people would post all sorts of junk, but that doesn't really happen because of this reputational thing. It's really bad for you to post junk. Now, there are people who have no reputation and don't care. Crackpot people in the world. And they did start to post stuff on these things. Like, I have a theory that if you would do something different, gravity would change directions. You know. And so the archive system eventually adopted an endorser system. So you have to have someone who's been vaguely approved to do this endorse your paper before it can go online. It's a very loose system. It's just meant to stop people who want to send in their same crazy thing every day. Now, not every paper does end up in the peer-reviewed literature. And an example from my own history is a submission that I sent in 2001. I put it on the archive at the time that I sent it into a journal. This is a paper that has nothing wrong about it, but when I sent it into the journal, it was talking about things people weren't talking about yet. And so the first reviewer I got was like, what is this about? I don't understand why you're even interested in this. And the second reviewer felt the same way. And by that time, it was a year after I'd written this paper, and I decided, okay, the field is moving on. I'm not going to put any more time into this. Besides, everybody I know already read this paper. It's already out there. People are talking about it. So I just stopped trying to put it into the peer-reviewed literature. It still exists here. It has 132 citations. People still read it. It never went in through the peer-reviewed literature. So it didn't count in my tenure case, but okay, I didn't really need it. Maybe in the future, people won't need that system at all. That's one of the things that I think is we're really moving toward. So the archive is this big, fascinating thing. I encourage you to go take a quick look at it. I mean, of course, most of these papers aren't papers you're going to want to read because they're super technical things about hyperspace, algebraic geometry, or whatever. But it's really cool to kind of see how simple it is. It really hasn't changed very much. Only thing that's happened is more categories have been added to this thing. And if you look now, it will say up here at the top, this is open access. Anybody can have this stuff to 917,955 e-prints in physics, math, computer science, quantitative biology, and quantitative finance and statistics. It's moved from underneath this guy's desk at Lawrence Livermore National or Los Alamos National Lab to the library at Cornell University. Right, so it's become a little more official, but it's still a wide open thing. Very cool. They've started to do things on it that you would never do in a journal. Like they actually search these to find plagiarists. And they find them. What they learned, which no one would admit before this, is that there's an enormous amount of self-plagiarism. And it comes in the form something like this. People write an article, they are always writing articles about galaxy clusters, for example. That's one of the things I work on. And there's always a part of the paper that's like describing what a galaxy cluster is at the front. And you need the same thing every time. And so people actually put the same thing in every time. Exactly the same thing a lot of times. And this is something that nobody even knows what to think about. Should they do that? Is it really bad or not? There's not really a community consensus about it, but they know how often it happens because they study it. Okay, so results are now more open through things like that. Open peer-reviewed publication of results didn't protect me from 6 years of fruitless labor in the desert, right? So what could happen to the practice of science that would be better than just having open peer-reviewed publication of results? What we could do is to focus on data. So now everybody puts out their results. Those 15 experiments that saw the same thing wrote papers about their results. But they didn't let us look at their data. They only let us see their interpretation of their data. So one of the things that the modern world has enabled is the possibility of asking people not only to say what they think about their data, but to actually give everybody else their data. All right? So open data is the thing that's coming. Reproducibility has always been the hallmark of science, this idea of nullius in verba, take no one's word for it, find out for yourself. After all, this system isn't that. It's taking other people's word for it, right? The way to open and get back to this is to take the data that are obtained, often in very expensive ways, and make them available to everyone else. So, for example, I worked on this project called the Sloan Digital Sky Survey. We spent about $70 million over a period of 10 years with 200 scientists putting together this enormous data set. If we had done that and then just written some papers about it, that would have been a terrible shame. Because we did all that effort to gather that data. We should give the data to everyone, along with the papers that we want to write about it, right? So open data allows replicability. If we didn't do that, somebody else would have to spend $70 million to reproduce our results. And that seems dumb, right? So in all these cases, if it's possible, all the data should be shared along with the results so that other people can learn from the data, either confirming what we already concluded or learning things that we never imagined were possible. Or they could, of course, find out that we were really wrong. So open data is the next really big thing in science. And it's another media thing. This is possible to have open data because it's possible to move data around so freely through the technological systems that exist. This project that I mentioned a little bit before, the Sloan Digital Sky Survey, was one of the first great open data projects, and it still is often held out as an example of that. It was done on this ridge in southern New Mexico. This little plateau below here is about 2,000 feet below this. It drops off another 3,000 feet to White Sands Missile Range down there. Really beautiful place, lots of elk roaming around and so on. This is the telescope that we used in order to do this survey. We built it specifically for this purpose. It took about 30 terabytes of data, which at the time was a terrifying amount of data. And today you could hook it up to your laptop in a little box about this big. Right, so the ability to move data around has really made this possible. What we did is we took pictures of the whole sky, of the whole northern sky, and then we actually measured distances to about 1 million galaxies. We put all this data together. It's all out there on a public web server. You can all go and download it right now. Want to do astronomy? Go download the Sloan data. Right, it's all there. What came out of it? This is a list of some of the publications that came out of it. Okay, there's no way you're going to read that. That's not the point. The point is that we published about 1,000 refereed articles. Meanwhile, the rest of the world published 9,145. So what we did got magnified by a factor of 9 by just giving the data away to other people to let them do more. These papers, as of today, have been cited 188,728 times. So they've really contributed to this flood of interchange of information. And that happened because we gave the data away. Open science is the best way to enhance scientific impact. It should become the cultural expectation, so that if you're a scientist and you discover something, you must give your data to other people. I mean, that has to become the expectation. And Perhaps a way to make it the expectation is for all federally funded science where you have contributed money to pay for that science at least should be required to give out its data. Okay, so that's something that I think is coming. It's something that is enabled by new media. It wouldn't be possible if we didn't have the kind of computer networking systems that we do. Let's see. I was going to talk a little bit about amateur science too. All science was originally done by amateurs, and Stonehenge is probably a great example of that. As we learned, professionalization of science took place in the 19th century. William Whewell actually invented the name a scientist. We need very much a name to describe a cultivator of science in general. I should incline to call him a scientist. So that's the phrase where it was invented in this book. I think everybody loves science. You know, there's areas of science that are practiced seriously by lots of people, especially ones that have to do with the natural world, like birding and mountain climbing and gardening and so on. And all kinds of people participate in science in all different kinds of ways, both personal and professional. And I'm going to skip over just a little bit here just to show you about what some of the ways in which people contribute to science in what become professional ways. This is a guy named Snowflake Bentley. He lived in Vermont in the early part of the 20th century, late part of the 19th century. He invented cameras which were designed to take pictures of snowflakes. And he stood out there in the snow and made volumes of pictures of snowflakes. You can still buy this book. It's really beautiful. It shows you all the different kinds of snowflakes, and there are many more than you know about. And by being tireless, by putting in a professional level of effort, he was able actually to make a professional level contribution to our understanding of snow. But most amateur scientists can't do that. They can't put in that kind of level of effort. And so I want to talk about two ways in which amateur scientists use new media to come together and bring together each of their small efforts in order to create a professional level contribution to science. The first one is something called the Audubon Society's Christmas bird count. This is something that began in the year 1900. It was begun as an alternative activity to what at the time was called the side hunt. So on Christmas Day, in this period of time, many people would go out with guns on Christmas Day and shoot as many birds as they could. That was what the side hunt was about. It was an activity thought to be fun. Probably is fun for a lot of people, I don't know. At any rate, people in the Audubon Society didn't want to do that, so they decided we'll go out instead and count all the birds we see. We won't shoot them, we'll go out and see them. So in 1900, 27 people counted 18,000 birds. In 2008, about 60,000 people counted in 2,000 circles and found 57 million birds. What this is doing is creating an irreplaceable annual study of the long-term populations of birds. You can't do it with just professional scientists because there aren't 60,000 professional scientists. You need volunteers. This is a classic crowdsourcing kind of experiment. Another project that's like that is called the Galaxy Zoo project. I told you that the Sloan Digital Sky Survey took images of many galaxies, 100 million galaxies. So I have some graduate students, but I couldn't ask my graduate students to look at the pictures of 100 million galaxies. You know, it just would take them too long. So what we did instead is to create this Galaxy Zoo project and take all of those images and put them online and let anyone look at them. And in the Galaxy Zoo, more than 150 million classifications were done by volunteers who came in and said, sure, I'll look at a bunch of images and tell you what I see. Some important new details about galaxies were learned in this citizen science project, and a really interesting, tricky bias was uncovered. So let me take a few minutes to show you a few results from these things. This is a map showing all the count circles that are used in the Christmas bird count. You can see that the central part of North America is really buried in them. This little spot over here, that's about where we built our cosmic ray experiment in western Utah. There's nothing out there. All right, so nobody's counting out there either. These are spreading all over the globe now as well. It's not just in the United States. Just to give a simple example of how things have changed, this is Christmas bird count data from about the time when I was born of bald eagle sightings in Christmas bird count circles. Have you ever heard about DDT? It was a pesticide that was used in this period of time that would actually make the shells of birds' eggs very fragile. This led to collapses in the population of birds like the bald eagle. And at this time, they were at about their nadir, the lowest point that they reached. Now, if you look at what's happening now in 2002 and 2003, there are bald eagles all over the place. Right? This is the kind of data we wouldn't have if 60,000 people didn't go out in the cold around Christmas Day and count all these birds. We wouldn't know what that population was. This is a really important, serious piece of science. You can look at the changes in the population of a species like a house sparrow and see that there are really long-term changes going on, measured pretty accurately. And people can wonder about those and see whether they want to do something about them. Let me show you a little bit about Galaxy Zoo. This is a project with a much fancier kind of interface. So this is the Galaxy Zoo project, which is now doing a lot of other things, not just galaxy projects. But let me show you what kinds of things they did. They wanted people to look at these galaxies and be able to classify them. Are they spiral galaxies, which are blue, or spirals, which are red, or elliptical galaxies like this? They would give you a little training, show you these different classes, and then ask you to start looking at images and classifying them. Galaxy images can be really beautiful, and part of the fun of participating in this project is to look at a bunch of different galaxy images and see how different they all can be. There's a really beautiful recent collision of galaxies there. And then what it would do is give you a little interface where it would say, okay, here's a galaxy. Tell me about that galaxy. Is it an elliptical galaxy? If it's a spiral galaxy, does it spin around clockwise, or does it spin around anti-clockwise, or is it edge-on and unclear? And you just look at a galaxy, you push the button, you get another galaxy, you look at another one. I mean, if you're going to play Candy Crush, you might as well play Galaxy Zoo. It's almost as interesting, right? And that was the idea, that you could put a task like this in front of people and do something interesting. This clockwise and anti-clockwise one is a particularly interesting example. Now, if you have a Copernican worldview and you don't think there's anything very special about the Earth, you would imagine that just as many galaxies would go clockwise as counterclockwise. Because, like, who would pick which way they should be, right? But it turns out that if you ask people to go out and look at the galaxies on the sky and count how many go clockwise and how many go counterclockwise, they don't get the same number. Now, that's weird. It could even be a really great scientific discovery. Remember when I started, I said one of the things you should be aware of is really weird things. And this was a case where it was clear that many people did the exercise and got that answer. But there seemed to be something wrong with it. So we used Galaxy Zoo to show what was wrong. Basically, the idea was we gave people these galaxies and let them call them clockwise or anti-clockwise. And then we gave them the same galaxies again in images that were flipped. So we knew we had flipped the images. And in both the original images and in the flipped images, people found more clockwise than counterclockwise. So people have a bias towards seeing clockwise in galaxies. And you could prove it by just testing it on all these people with all these galaxies and seeing over and over again that any group of people has that same preference. So it's not real in the sky, it's real in the people. And you could test it and prove that it was real in the people by having a tool like this. Something, again, that we never could have done with graduate students because you just can't hire enough graduate students to do that kind of test. Okay? So that was a really cool experiment, the large-scale spin statistics of spiral galaxies in the Sloan Digital Sky Survey. This one was published just 3 or 4 years ago. And in it, they thank all the people who did the work. They don't put all 100,000 people in the author list, you notice? But they do thank them down here. Ultimate thanks must go to all the volunteers that made the Galaxy Zoo possible. Not only does this include the 100,000 users who personally identified hundreds of galaxies, but all the other people who participated. So this is a way in which modern media are enabling everyone to participate in science in a real substantive way. In the peer-reviewed scientific literature, people are contributing to this. And they couldn't do it if it wasn't for this kind of new media. There are many examples of this going on, and they're even beginning to spread into fields like the humanities. There are a number of famous scientists and writers whose letters are being put online, scanned, and they're actually really hard to read. So you can go be a volunteer and try to read them and then type them in to transcribe them and contribute to a digital version of all the letters of someone like Alfred Russel Wallace. Things like that. So there's lots of these citizen science projects emerging. Couldn't have happened 10 years ago, certainly not 20 years ago, and now they're becoming increasingly important. So I think they're really cool. Some other discoveries, the discovery of green pea galaxies, which are pretty cool. And then, even things like the journal Nature are beginning to recognize this. So this is an editorial published recently in Nature about the Christmas bird count, a model to be emulated in distributed volunteer science. Researchers should think creatively about whether the data they need or the crunching or sorting they must do can be outsourced to members of the public. And while they're at it, perhaps they should also consider joining one or more citizen science projects themselves. I have done the Christmas bird count for the last 12 years. It's always really cold. We start at 4:30 in the morning counting owls, and we go right into the afternoon. And it's a great way to end the fall semester. You get out of class and you go spend a whole day outside thinking about something absolutely different from what you've been worrying about for the last few weeks. So if any of you want to do that next fall, send me a note. We're always looking for bird count volunteers. The thing we perhaps need the most are sharp young eyes and ears. You don't have to know all the birds. You just have to say, oh, look, a bird, right? And we'll tell you what it is. Maybe you'll learn something along the way. Okay, so those are some of the ways in which new media has really affected science. It spreads much faster than it used to. The data is being given to everyone, and people are able to participate in ways that they never would before. Those are all changes that have happened totally in my career. When I started, none of them were present. Now they're becoming the dominant thing. So we're actually, we're watching real changes happen, changes that didn't happen for 100 years before that. And I think that's pretty cool. So, all right, I'll stop there. Has any of you ever done a project like this? Contributed to some kind of collective project? In school? Sometimes schools do this too, like stream monitoring or something. Yeah?
A university, I think it was probably something Harvard-based and in Boston, came to our high school and introduced us to this program where they had designed a game where you could go on and contribute to mapping out neurons in the human brain.
Yep.
And there were far too many for anyone
Yep.
to do in a single run.
Yeah, so people are doing many projects like that. There's a famous one called Fold It, where you try to figure out how proteins actually fold, and it's like a puzzle. So in fact, anyone can learn to be really good at figuring out how proteins fold, and it's a problem that uses people's minds more than their reflexes. Yeah.
Do you think it's a problem, especially in social science, when researchers go into like a project wanting or like pretty much knowing what's going to be the outcome, so then they're more susceptible to like skewing data?
Sure.
For example, there was like a study where they tested people who were not actually insane, but they put them in silence, and the people who were assessing them pretty much made them seem like they were insane.
Yeah.
I was like seeing how you did the 15
Yeah, right.
that like had the wrong data. Do you think that's a problem?
Yeah, it absolutely is. I mean, so science, a model of science is this sort of hypothesis-driven model. You have an idea of what will happen in the world. You design an experiment to test it. But of course, you did come in with that idea, and you tend to like that idea. You can tend to believe it must be true. So one of the most difficult things as a scientist is to fight against confirmation bias. It's a very famous form of human cognitive bias. You see it in all kinds of places. We want the things we expect to be true. And so a lot of your training as a scientist is to learn what methods can you apply to yourself. How can you yank yourself back from that terrible mistake? Nobody wants to make mistakes. Scientists most want to be right, but it's not hard to be pulled in that direction and to have that kind of thing happen to you. So if any of you become scientists, really, it's the most important thing to be right. It's terrible to be wrong, even if you want that thing to be right. You know what I mean? It's much better to find out the truth. So anyway, there's lots of methods to try and reach that. Okay?
Much better to find the truth.